Hello, I am Syntax Sugar, and today we'll be looking at the Monty problem. So, this problem is a probability puzzle which was named after the TV host Monty Hall, and it was posed as follows in the Parade magazine. Suppose you're on a game show and you're given the choice of three doors. Behind one door is a car, behind the other is goats. You pick a door, say number 1, and the host, who knows what's behind the doors, opens another door, say number 3, which has a goat. He then says to you, do you want to pick number 2? Is it to your advantage to switch your choice? So you can imagine you've picked door number 1, and then he's asking you, the host is asking you if you'd like to switch to number 2. So is it advantageous for you to switch to door number 2, given that door number 3 was open and you can see it's a goat now? So I'll give you a moment to give it a shot before I start. Okay. Bayes rule. So we're going to go through this problem first by looking at conditional probability. So we know that the probability of A given B is equal to the probability of A and B divided by the probability of B. So you can imagine it kind of like you're zooming into the subset of event B happening, and that's kind of why the division is happening here with the probability of B. And a question that may come to your mind is, what is the relationship between the probability of A given B and the probability of B given A? So let's look at the probability of B given A, and we can see it's identical except that the denominators switched here from probability of A to probability of B. So I want to get the probability of A and B now, and we can do this by multiplying both sides by the probability of A, and you get this. Probability of A and B is equal to the probability of B given A times the probability of A. And then, since we have this, we can substitute it into our first equation, the probability of A given B, and we can get this one. The probability of A given B is equal to the probability of B given A times the probability of A divided by probability of B. And this is Bayes' rule, or Bayes' theorem. And another form which we're going to use is we're going to substitute probability of B at the bottom with the sum of the joint probabilities. So we'd say the probability of B and A and the probability of B and not A, which is this symbol. And then we can switch these joint probabilities into these forms also, these probability of B given A times the probability of A, as you can see here. Okay, so now we're going to be applying the formula to our problem. So we let event A be that the first door is a car. Behind the first door is a car, B the second door is a car, and C the third door is a car. And let C small be the event that the third door is opened, revealing a goat. And all we can do now is, all we need to do is define our probabilities based on what we've seen. So the probability of A is also equal to the probability of B is equal to the probability of C, which is equal to 1/3. This is at the beginning, so don't mess up these prior probabilities with your final one, the posterior, which is the later one. And now we want to know that the probability of that door A has a car, given that C is opened. And we can see this in this equation, which we just used, but it's a lot bigger now since we're adding about 3 possibilities that we have. So it's the probability that door C is open, given that A is a car, times the probability of A, and then we see the same probability here, and then times or added to the probability that C is open, given that B is a car, times the probability of B, and C given that C is open to be a goat, and C is the car, times the probability of C. So what we don't know are these probability of C given A and C small given A, and the probability of C small given B, and probability of C small given C. So let's look through them. So when A is the car, yeah, we can either door B or door C could be opened. It doesn't matter which one, since they're both goats. So it's a 1/2 probability that C is open, given A is the car. And the probability that B is opened, the probability that C is open given that B is a car, and we're holding A, is 100%. It's 1. Since we're holding A, he can't open A, and since B is the car, he won't open the car, so it's 1. And then obviously, since it's a car, if it's a car, he's never going to open C, so that's 0. And now we can just calculate it. So we get this form, and you can do it in your head or you can do it in paper, and you're going to get 1/3 for the probability of A given C, that C is opened and is a go. But the probability of B given C small is actually 2/3. And this is the trick that many people fall into. You would assume since there's 2 doors, it'll just be 1/2, 1/2. But actually, when you do the math and you do the probability, you can see that probability at its B, given that C was open and it was a go, is actually 2/3. Almost, at double the probability that it's A, given that C was opened. And really paradoxically, I'd say, it gives opening door C gives you information about door B, but not about door A. So you're better off switching than staying at your position to answer the question. And finally, Bayesian statistics is a really big topic, and I didn't use it to its fullest extent. It was just a use in a probability puzzle, but I think this is the beginning to using it in more advanced applications. And finally, I want to give you a problem to solve on your own. Here, you get 3 prisoners, A, B, and C, are in separate cells and sentenced to death. The governor has selected one of them at random to be pardoned. The warden knows which one is pardoned, but is not allowed to tell. Prisoner A begs the warden to let him know the identity of one of the 2 who are going to be executed. If B is to be pardoned, give me C's name. If C is to be pardoned, give me B's name. And if I'm going to be pardoned, secretly flip a coin to decide whether to give me the name B or C. The warden gives him B's name. Prisoner A is pleased because he believes that this probability of surviving has gone up from 1/3 to 1/2, and it is now between him and C. Prisoner A secretly tells C the news, who reasons that A's chance of being pardoned is unchanged, but he is pleased because his own chance has gone up to 2/3. Which prisoner is correct? So this problem is a lot like the Monty problem, and some would even say identical. So you can give it a shot. And as always, I thank you for listening, and any feedback is appreciated.